Hello everyone, I'm Norman Wahlberger. In today's famous math problem, we're going to look at the question, are all true mathematical facts provable? This is usually associated with the work of Kurt Gödel and logicians following him. He showed in 1931, in the context of so-called formal systems and axiomatic frameworks involving statements and theories as mathematical objects, that in an appropriate formal system there are true statements that can't be proven. He was using here the basic logistic kind of framework that had been established by Russell and Whitehead in their monumental treatise Mathematical Principia in 1910. This theorem of Gödel, and I put theorem in quotes a little bit, had a big influence on mathematicians, and it reshaped their understanding of the subject. So much, I would say, that it really colors 20th century mathematicians' view of what mathematics actually is. While Gödel's argument was rather complicated and hard for mathematicians to follow, later mathematicians, Turing and Post in particular, gave simplified versions of the argument and restated the theory more in line perhaps with computability questions. And I think they sort of showed that the essence of the argument is really contained in a self-referential kind of statement along the lines of this. You've all probably seen this statement. This statement is false. Okay, so you're shown the statement and asked, well, is this a false statement or a true statement? And one has difficulty deciding that because of the self-referential aspect of the statement. So that's sort of the kind of idea that's ultimately involved in Gödel's theorem, along with use of Cantor's diagonal argument. So when you actually want an example of a theorem which is true but can't be proven, usually you end up with some kind of perhaps disappointing example, and you're getting some statement that's more or less something like this. So as I said, Gödel's result really had a very significant influence on 20th century mathematics. The idea now, as a result of his work, is that mathematics swims somehow in a sea of ambiguity. We can't really be sure about things too much. It all depends on your axiomatic position. Gödel was working within a framework, often attributed to Hilbert, of sort of axiomatic systems where you posit various assumptions to build your theories. Theories are just something that's built up from various axiomatic positions. And I think one of the really main consequences is that generally mathematicians started feeling, well, maybe foundational issues are best left to the logicians. Well, the logicians are the people who are specializing in this, and we're going to keep these things at arm's length. It's a very negative development in my view, okay? Because it means that mathematicians became loath to really roll up their sleeves and get down to understanding foundational issues, of which there were many, many serious ones that we should have tackled in the 20th century. So the beauty and order that characterized 17th, 18th, and 19th century mathematics to a large extent was in the 20th century replaced by some kind of gray, murky arbitrariness. I think this has been a very unfortunate development, and to be honest, I don't have a lot of sympathy or belief in the validity of Gödel's arguments. I'm sorry, but someone has to say this. Okay? I don't think it's real mathematics, and I don't think it's particularly, really truly reflecting the mathematics that is out there. It represents a misunderstanding of what the foundations of mathematics really is about. So in my opinion, Gödel's work is actually between mathematics and philosophy. It's certainly interesting, and it suggests, I think, from a philosophical point of view, that a formalist approach to mathematics, which was basically championed by Hilbert, is rather limited. The idea that mathematics is just a formal game that you can play with symbols and then create everything is just too limiting and too narrow a view. So why do I think that it's largely philosophical? Well, here's mathematics, and we have to recognize that around mathematics is meta-mathematics, where we are talking about mathematics. Well, the words that we use are not very well precisely defined. So unless you're very careful, notions such as theories, axioms, statements, truth, provable, logical systems are very hard to pin down. Very hard to say precisely what we're talking about when we use words like this. In my view, these are meta-mathematical concepts and not mathematical ones. And the reason why Gödel's result should be brought into question is because I believe he was trying to push these concepts from meta-mathematics into mathematics. He was acting on them as if they were mathematical concepts, like the concept of a prime number or a square number or divisibility or something like that. Whereas in the reality is these concepts are much more murky and they really live more in meta-mathematics. All right, so that's my point of view. We're going to talk a lot more about this kind of thing in the Math Foundation series. I'm going to give a much broader critique. I just want to give you a general framework. So basically, I reject ambiguity. To me, mathematics, there's absolutely nothing ambiguous about it at all. It's completely cut and dried, black and white. Everything fits together completely, perfectly, and correctly, ka-chunk, ka-chunk, ka-chunk. Okay? It's actually a fabulous edifice that we are privileged to study. And our own particular positions, philosophical or theological, have really nothing to do with the mathematics itself. And we should not let them interfere with our study of this subject. All right. So that's my position. That's the kind of mathematics that I'm going to be showing you is possible in my Math Foundation series. So I'm going to present a lot of evidence for this quite different point of view on this very important issue. All right, but I'm still very interested in this question. Famous math problem 17, are all true mathematical facts provable? In my view, this is a difficult but solved problem. And I'm going to show you a solution today. So this is really a meta-mathematical question, though. We have to be prepared for a meta-mathematical kind of answer, but the answer in my view is no. Okay? It is not the case that all true mathematical facts are provable. In other words, there are true mathematical facts which cannot be proven. Almost surely. So there's the kind of meta-mathematical aspect of this. And I'm going to give you some explicit examples that are completely separate from Gödel's work and Gödel's thinking. Okay? And I'm interested in giving you examples that you can really see right there in front of you, and you can say, yep, this is for sure, almost for sure true, perhaps, but I just don't know how to prove it. And our main tool is going to be something rather modest. It's going to be a procedure to solve a very relatively simple equation. X squared equals 19. We'll have a look at how you calculate a square root of 19. There's a classical algorithm for calculating a square root, and I talked about that in my Math Foundations 49 video. It's called How to Find a Square Root. It's the ancient Vedic method that used to be quite well taught. But I'm not going to use that today because I don't want to go over that method. I want to introduce a rather more simple, direct, naive method, which is somewhat less efficient. But the only thing we really need for this argument is some procedure for calculating an approximate square root. So here's a method. Step one is to find a natural number or integer, n0, such that n0 squared is less than or equal to 19. But n0 plus 1 squared is bigger than 19. So we're looking for a natural number or possibly 0. So 4 will do the trick because 4 squared is less than 16, but the next number, 5, is bigger than 19. So that's the first number that we get. We'll call it n0. Step 2. We're now going to look for the largest digit n1. Now it's going to be a digit one of the 10 numbers between 0 and 9. Such that if you look at the decimal with n0 as the integer part, then dot n1, if you square that, you're less than or equal to 19. So we're looking for a decimal of the form 4 point something, whose square is less than 19, and we want this n1 to be the largest such digit. And we can check that 4.3 works. So if n1 is equal to 3, then 4.3 squared is in fact less than 19, but 4.4 squared will be bigger than 19. So you just run through all the various possibilities if you need to, okay? Starting with 4.0, and then going up, 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 until you get to a number which is bigger than 19, and then you choose the previous one. Okay, once we have the digit n1, to get the digit n2, what are we going to do? We're going to find the largest digit n2, also from the same range, so that n0 dot n1 n2 squared is less than or equal to 19. In this case, we already have 4.3, so the n2 is going to be the next decimal. So we're looking for the largest digit that we can put there, so that 4.3 n2 squared is less than 19. And it's 5. And we continue this way. So we create each decimal one at a time just by looking at the digit, which is as big as possible, that we can add, still maintaining this condition that we are less than or equal to 19. It's a surefire way of creating a sequence of decimal numbers which are getting closer and closer to solving this equation. We know that this equation doesn't have a rational solution, so we're not actually ever going to finish and get a true square root, but we can get closer and closer and closer to having this property. So it's only this algorithm that we are going to need to give an example of a true mathematical fact which can't be proven. Alright, so if we carry on this way, then we could, with some patience, verify that the first 101 digits after the decimal point are going to be as follows. So we can get 4.358898943354067355223698198385961 565913700392523244493 689034413815955 73282031580 565-615-915585194452690. And we could keep going. And every subsequent digit that we create requires more work generally than the previous one. The numbers involved are bigger, and it's pretty clear, at least up to this point, that there doesn't seem to be any rhyme or reason to these digits. It's very hard to predict what the next one is going to be. It's almost like a random sequence. It's not random because it's given by this algorithm, but it looks quite random to us. Okay, now I'm going to make a definition. This is, I think, an interesting definition. Okay. It's that the decimal number obtained by computing all the digits from n0 up to nk will be denoted square root of 19 with a k down here in the sort of left bottom corner. Okay, so for example, square root of 19 with a 0 here, that's going to be just the integer part, which is 4. If we put a 1 here, it means that we're going to go all the way to the first digit, 4.3. With a 2, we'll get 4.35. With an 11, well, we're picking up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The first 11 digits included past the decimal point. So this is a finite decimal. This decimal number is equal to square root of 19 sub 11. Square root of 19 sub 101 is the number that I've presented here. Okay? There's no 3 dots here. We've just run the algorithm up to that point. We've computed 101 digits to the right of the decimal point. That number is exactly square root of 19 sub 101. Okay, it's an interesting definition. All right, note carefully that square root of 19 with an infinity under here is not defined, because we don't believe in ghosts, fairy tales, or the ability to make an infinite number of computations. You can make computation to 100 decimal places, to 1,000, to 1,000,000 maybe if you have a really good computer, maybe to 1,000,000,000 if you have a very, very strong computer for a long time. But going to the end of time and getting all of them, no, that's just not possible. And we're not even going to pretend that we can do that. Right? We're interested in complete honesty here because this is mathematics, isn't it? Right. Okay, so here I'm going to present you with some, what I claim are true or almost surely true facts. The first one is relatively simple, that the last digit of the square root of 19 sub 10 is not 8. In fact, on the previous slide, it's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The last digit of this is the 10th digit, is actually a 5. So it's certainly true that the last digit of this thing here is not an 8. And the second true statement is that the last 10 digits of the square root of 19 sub 100 are not 88888888888. Again, that's obvious. We've already written down what square root of 19 sub 101 are. We've seen that it doesn't end in a string of 8s. This is a self-evidently true fact, which we are sure of because we've computed it. So at this point, we are still sure of the validity of these facts. Now the third statement, the last 100 digits of square root of 19 sub 1,000 are not all 8s. This is a fact that I can verify to you is correct because I've asked Wolfram Alpha to churn out the first 1,000 digits of square root of 19, and it has, and I've looked at it, and I've looked at the last 100 digits, and I can assure you that they are not all 8s. Okay, so these three facts are certainly true facts, and we can prove them by actually making the computations. Or asking a machine like Wolfram Alpha, which has already made the computation or can make it very quickly, what the situation is. Okay, now I'm going to go a little bit further. Something in the very same spirit, but with bigger numbers. So the last 1,000 digits of square root of 19 sub a billion. Okay, here's 10 to the 9th. It's a billion. So we're going to calculate square root of 19 up to 1 billion decimal terms. Nobody has ever done this. Okay, I think the most that square root of 2 has been calculated is, in the orders of tens of millions. I could be wrong, but that's my estimation. So almost for sure, no one will have computed the square root of 19 to 1 billion. Well, but it's not impossible to do this. Present technology, certainly you could probably aspire to doing that. And the claim is that when you do that and look at the last 1,000 digits of that number, that they are not all 8s. So I'm saying that it's not the case that the last 1,000 digits are all 8s. 8, 8, 8, 8, 8, 8, 8, 8, 1,000 times. It's almost surely true, right? Because the chances of all those digits being 8s, a whole string of 1,000 of them, are minuscule. That's just not going to happen, with a very, very, very high probability of being right. But we're not really sure until we actually calculate it. There's some very, very small probability that it could be true, that it could be that the last 1,000 digits of this decimal are in fact all 8s. But almost surely not. I'll bet my bottom dollar that's not true. Okay, now here's a more sophisticated version. For example, for any k, any natural number k, the last, say, 10 to the k digits of square root of 19 sub 10 to the 10 to the k are not all 8s. Let's consider this statement. All right, so for k equals 1, what is this? It's saying that the last 10 digits of square root of 19 sub 10 to the 10 are not all 8s. Okay, 10 to the 10, that's a little bit more than this one. So that's quite a big decimal expansion, 10 billion places. And we're saying that the last 10 digits of that are not all 8s. That's the case k equals 1. And in addition, for k equals 2, the last 100 digits of 10 to the 10 squared, with the square root of 19, are also not 8s. And for k, say, equal to 3, the last 1,000 digits of 10 to the 10 to the 3, square root of 19, are not all 8s. And so on. So we're saying for any natural number k, the last 10 to the k digits of this thing here are not all 8s. This is very likely to be a true statement. And the place I would worry the most about its non-truth would be when k equals 1. So when k equals 1, we're only talking about 10 digits. Then it's not impossible, within the realm of possibility, that the last 10 digits of this number just happen to be all 8s. I've just been unlucky in choosing the actual numbers there, and lo and behold, they were all 8s. So to prove this was true, I would have to actually check that. But I have to check more than that for the truth of this statement. I have to check that not only is it true for k equals 1, but it's also true for k equals 2, and it's true for k equals 3, and it's true for k equals 4, and it's true for all k. How is one going to prove something like that if it's true? Okay, it's very likely true. I think the probability of it being false is very, very small. But proving such a thing, I have no idea how you would possibly prove this. In fact, everything, conspires to suggest to me that you're not going to be able to prove this, because the nature of these digits far out in this decimal expansion are so mysterious in a way. There's no easy way of getting at them. Too much work is involved to be able to say something about them. So this is very likely a true fact that can't be proven, but we're not entirely sure. So most mathematicians who have worked in this area are reasonably confident that the sequence of digits associated to a square root of 19 is very likely to be normal. What does that mean? That's an interesting and important concept for us here. Normal roughly means that statistically it's like a random sequence, that there's no bias in it towards some digits or any combination of digits. So no digit is biased. In other words, in the long run, they each occur roughly 10% of the time. It's not the case that there's, consistently more 2's than there are 1's in the decimal expansion. Of course, up to a certain point, they're not going to be completely equally distributed, but as we get longer and longer sequences and count numbers of 1's, 2's, up to 9's, those ratios are supposed to get closer and closer to being 1/10 as we go out. But that's not just true for single digits, it should also be true for pairs of digits. So the combination 1, 3 versus the combination 5, 7, if you count how many 1, 3's there are and how many 5, 7's there are in the first million digits, then hopefully you should get both of them roughly 1/100th of the time. And then the same thing should occur for triples of digits and so on. So any string of digits of a certain length should be no more nor no less likely than any other string with the same length. So the probability of a string of 10 to the k digits being, say, all 8's that appears somewhere in this decimal expansion should be, well, 1 over 10 times 1 over 10 times 1 over 10, all together 10 to the k times, because there's 10 to the k digits that we're considering. So the probability of having such a long string of consecutive 8's should roughly be 1 over 10 to the 10 to the k. So for any natural number k, this is going to be a small number, but of course it's going to be still non-zero, because after all, in some string of 10 to the k digits, there's some pattern appearing, and any one pattern is just as likely as any other. So the normality of this square root of sequence is really an essential aspect of this problem. So we expect that if we're looking at something like the square root of 19 decimal expansion, that let's say you're looking for strings of consecutive 8s, that there will be places where you'll find strings of 10 consecutive 8s. And there will be places where you find strings of 100 or 1,000 or 1,000,000,000,000 consecutive 8s. It's hard for us to fathom that at some point in this sequence, there's likely to be a place where there's 1,000,000,000 8s in a row. In fact, there's going to be many, many such places. And billion can be replaced by trillion or a trillion to the trillion or any big number you like. So it's assuming, of course, that you can generate sequences of large enough size, then you can expect to get all kinds of strange substrings contained inside there. In particular, strings of 8s. So it's possible, it's not out of the question that if we look to the 10 to the 10th to the 10th to the 10th place, and then we look at the last 10 to the 10 to the 10 digits, that they all happen to be 8. There's some small but non-zero probability of that happening. So to make our statement even more likely to be true, let's just add a little bit even more freedom to things. So I'm going to say this is Norm's decimal conjecture. So here's a conjecture of mine. Okay. So it might be that things conspire so that the square root of 19 example that I gave doesn't work. That there is a string of 8s just where I said there wouldn't be. Okay. So to overcome that possibility, let me be a little bit more general. So let me claim that there is a prime number p with the following property. That for any natural number bigger than or equal to 1, the last 10 to the 10 to the k digits of root p sub 10 to the 10 to the 10 to the k, the last 10 to the 10k digits of this number are not all 8s. Now this is an incredibly safe statement to make because this is such a large number. Even if k is 1, we're still talking about 10 to the 10 digits. We're talking about 10 billion digits. The last 10 billion digits of this thing are not all 8s. That's the most radical of the various statements. The next statement is even less likely to be true because it involves not 10 to the 10 digits, but 10 to the 10 squared digits. Okay, so I'm willing to bet my bottom dollar that this is a true statement. Okay, I'm firmly convinced that this is a true statement. It's something that I have as much confidence about the truth of as I do of almost any theorem that's found in modern journals. In fact, I have a lot more confidence in the truth of this statement than if I open up a random mathematics journal and look at a random theorem. Okay, I have no way of even imagining how you could possibly prove this is true. First of all, this number here, this thing is so big, it's beyond your computing, and it probably will be for millions of years. And even if you could compute it, you need to compute this for all k, not just for k equals 1, k equals 2. Okay, so this is true but not provable, almost surely. But of course, the whole thing is not really mathematics. I hope we all appreciate it. I'm talking about meta-mathematics here. Okay, I'm not making a theorem here. I'm just saying, from a philosophical point of view, this is a mathematical statement which is very, very likely to be true and very, very likely to be not provable. Okay, so there's limitations to what we can do in mathematics. But hey, we knew that all along, didn't we? I mean, this really shouldn't bother us, and it really shouldn't have bothered 20th century mathematicians as much as it did. So there's limitations. So we can't do everything. So we can't know everything. Yeah, that's all right. There's still a lot that we can do, and there's still a lot that we can know. So as long as we do mathematics correctly, make sure that everything is tight, clear, logical, we can uncover many, many beautiful truths. In our next lecture, we're going to talk about a famous problem, that has to do with projective geometry. It's a problem that's quite interesting from the point of view of an artist. Very practical problem. It's to do with the perspective image of a square. What can a square look like if you project it onto a plane? I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.